The derivative of ln of x, or logarithms, it's not as complicated, but similarly with the exponential video, I'm going to start simple and then build through the rule as we go along. And as I expect with this video, you should be fluent with the chain rule, product rule, and quotient rule, because they will be in handy when you're applying to the derivative of further functions. So the derivative of ln of x is just 1 over x. So one thing to note is we will call this the argument. So whatever goes inside the ln of x, so whatever is inside this ln of x, this is called the argument. So the derivative of ln of x is going to be 1 over x. So I'm taking the argument to the denominator. Now let's look at an example. If I have 9 ln of x, what I can do is split the coefficients from the function ln of x, and I'm just going to derive the ln of x, because the 9 can just multiply with the derivative of what's inside. That's one of the rules of derivatives, which makes derivatives easy. You don't have to deal with the 9. You can just look at the ln of x, keep the 9 on the side, and multiply it by the answer. So y prime is going to be 9 times the derivative of ln of x. The derivative of ln of x is 1 over x, and then I can just simplify it to 9 over x. Let's look at another example. Pi ln of x, same thing. I'll split the pi from it, and then it's just going to be pi over x. So again, we're multiplying the derivative with the coefficient. In the case that you're faced with a function where the ln function where there's a coefficient inside the argument, so you have k of x, and we're still dealing with x to the power of 1 here, then the derivative is just going to be a 1 over x. So for example, you have ln of 5x, the derivative is 1 over x. You have p ln of 6x, the dp by dx is going to be 1 over x. And m equals ln of 70, the derivative is going to be dm by dt is 1 over t. So the idea is that the 5 and the coefficient here gets cancelled. An alternative way of seeing this is I can rewrite this using logarithm rules as an addition. So ln of 5 plus ln of x. And the derivative of 5 is just 0, and the derivative of ln of x is 1 over x. Hence why no matter what the coefficient is inside the argument, the derivative will always be 1 over x. So maybe whenever you're unsure, always use the logarithm rules to split this up. So then we can make it a bit more general. What if it's not just a coefficient? What if it's a whole function inside of ln of x? So what you're going to actually do is you're going to derive the argument, so whatever is inside ln of x, and you're going to multiply it by 1 over the whole argument itself. And it still works for f of x here. It still works for all the rules we did above. Just the first and the second can be generalized into this last one. So let's look at examples. So if I have this, the derivative, I'm going to take, this will be my whole u here. So this is the derivative of the argument, u of x. It's going to be 15x to the power 4. And then this is the argument itself, not change, the original one. So I'll just multiply them together. I'm going to simplify, and I'm going to get 5 over x. Now, an alternative method is to, again, as I did before, to split it up. So ln of 3 plus ln of x to the power 5. And again, using logarithm method. So all I'm doing, I'm not deriving yet. I'm just simplifying my expression. So then I can use the rules of logarithm, as I explained before. The first one's going to derive to a 0. The second one's going to derive to a 5 over x. So the final answer is 5 over x. Be careful that this 5 over x is not the same as ln of 5x, okay? So there are different rules in here. If the coefficient is outside the logarithm, then you keep it there. If it's inside, then it ends up disappearing, roughly speaking. Let's look at another example. If I have ln x squared plus 1, x cubed minus 1, again, it's much easier to actually use the rules of logarithm and split the division to subtraction, and then use the rule here for each one. So I'm going to derive the argument. So I'm looking at the first one. The derivative of the argument is 2x. And then this is the argument in the denominator, so x squared plus 1. And then I'm going to do the same thing for the other one, 3x squared, and then the argument in the denominator. And you can simplify further, but this is the best you could put it in. Let's look at using the chain rule here. So if I have the whole ln argument raised to the power of 3, I can do a substitution, or I can write u as ln of x, and so my function is now u to the power of 3. So using the chain rule, I know I need to do dy by du multiplied by du by dx. Now dy by dx is now going to be 3u squared times 1 over x. Bringing back the ln, I'm going to put it back here, simplify it further, and this is what I'm going to get. Now again, we can use some of the rules of derivatives. So I can use the product rule here. If I have x squared and ln of x, I'll use the product rule because these are two functions. And I'll just take u as it is, the derivative of v, which is 1 over x, so the derivative of ln of x, and then the derivative of the second one, 2x with the original. And these two cancel out, so I'm going to end up with x plus 2x ln of x. Another example, let's say I have this. You can pause the video and try it yourself, and I'm going to get this is what I'm going to get, so you can check it yourself, and I'll simplify it to this. Now be careful that the x squared and the x don't cancel out, because the denominator here is enclosed inside a bracket. You can't access it, basically. So I'm left with 2x squared over 2x plus 3, and so on. So we're still using the product rule. Just make sure that you are deriving everything correctly in the correct order. So for example, notice that the derivative of v, which is this ln, is going to be the derivative of the inside, which is 2, divided by the argument itself, 2x plus 3. So that's the derivative of ln, and that's the original u. One last thing, I have two examples on quotient rule. So if I have f of x is this, I can use the quotient rule here. So I know I said you can avoid the quotient rule, but that's if it's inside the ln, the argument. But there's nothing in the argument of ln, just the x. So I can use the rule here. So the v is just ln of x. The derivative of the numerator is 1. The original numerator is just x, and the derivative of the denominator is 1 over x, and then the denominator squared. Be careful that the 2 has to be enclosed for ln of x and not for the x only. Then I can simplify this. These x's cancel out, so I'm left with ln of x minus 1 over this. An additional thing you could do is split this up if you wanted to simplify it further. So the ln of x to the power of 2 goes to each of these values. It's like undoing a fraction. So you have this and this. I just gave the ln x to the power of 2 to each one. And then I can cancel these out. I'm left with 1 over ln of x minus 1 over ln x squared. One last example, if I have this, you can pause and try this on your own, and this is what you're going to get, the original of the denominator multiplied by the derivative of the numerator. The derivative of the numerator is just 1 over x, because this derives to a 0. And then times the numerator originally, and then multiplied by the derivative of the denominator, which is 2x, and the denominator is squared, so don't forget the original square. I can simplify this, so the numerator here, the first argument here, this cancels out, and I can multiply this out, so I get 2x plus ln 2x ln of x, but then it's a negative, so the negative goes to each one, so I have a negative 2x and negative 2x ln of x. And the first one simplifies to just an x, so you're left with 1x here. And then we are going to simplify this further. X minus 2x is just negative x. And if you want to as well, you can split the fraction, and these will cancel out. You're left with negative 1 over x cubed minus 2x ln of x over x to the power of 4. You don't have to do this additional step. Sticking to this is okay. This doesn't serve much in terms of simplifying. So hopefully this was clear. Similar to exponentials, you need to make sure that you practice enough of these rules in order to get to these steps. So start simple and then progress further.